Solution of electrostatic problem is generally obtained by solving Poisson equation or Laplace's equation, which is not always very easy to solve. Keeping this in mind, Lord Kelvin developed a method called the method of electrical images. The method was developed in similarity with the image formation problem in geometrical optics. This may consider a point charge. A point charge Q is placed in front of a conductor. If it is a positive charge, then there will be negative charges induced on the conductor, and if it is a dielectric, then charges will be the dielectric will be polarized due to the presence of the charge. We call this as inducing charge, and the charges will be induced on the material body. If you are interested to find out the potential at any point, the potential as per superposition principle will be partially due to this inducing charge and partially due to the induced charge in the conductor or in the dielectric. Since it is not very easy to take into account the effect of induced charges. In method of images, what one does, one replaces the effect of induced charges by one or more suitable point charges of suitable magnitude and placed suitably, so that it satisfies all the boundary conditions of the system. So uniqueness theorem says that the solution so obtained is a solution of the actual problem, and at most one can add a additive constant, add a constant. The basic principle is that if you want to find out potential in this region, this is the surface, separating surface, then the image charge should be placed on the other side of the surface. And if one wants to find out the potential or field in this region, then the image charge should be placed in that region. So we define image charge as a set of points, as a single charge or a set of point charge, which placed on one side of the surface produces the same same potential or field on the other side of the image as produced by the actual electrification of the material. We shall in the first lecture we shall apply this method to a plane grounded a point charge in front of a grounded conducting plate. This is the conducting plate, and this conducting plate, so as to eliminate end effect, we assume that the plate extends extends up to infinity on either dimension. We assume the plate to lie in the z is equal to 0 plane, and we have a point charge of magnitude q which is placed at a distance d from the plate. Now we drop a perpendicular from the point A where the inducing charge is situated on the plate and treat its foot as the origin. So the conducting plate lies in xy plane, and the coordinate of the inducing charge is a0, 0, d. We want to find out potential at a point P having coordinate x, y, z with z positive. Since we are interested in finding out the potential above the plate, we place an image charge of magnitude q prime at B. By symmetry of the problem, we found that the image charge should be placed on the negative z axis. So the coordinate of the image charge is assumed to be 0, 0, minus d prime. This image charge accounts for the charge induced on the conducting plate, and so far as the calculation of potential at an external at point P is concerned, it is the combination of potential due to the charge Q at A and charge Q prime at B. Our aim is to find out Q prime and D prime by applying the suitable condition. Now, what is the boundary condition of the problem? The boundary condition of the problem: 1. Phi at z is equal to x, y, z is equal to 0 is 0, because the plate is grounded, as grounded. This is this count. Second point, phi e must go to 0 as r goes to infinity. That is, the potential at a large distance from the plate is 0. Thirdly, phi Laplace's equation is satisfied at all points except A, because A is the location of the point charge. At this point, Poisson equation will be satisfied, and all other points Laplace's equation will be satisfied. These are the boundary conditions. Now, potential at A, potential at P, which is in Cartesian, is given by phi at R is equal to this is Q charge is placed at A, so it is AP plus BP this vector is D vector, and this is R vector, this is R vector, so this much is R minus D, and this is minus D prime vector, so this is R plus D. If we write it in components form, this is so K is 1 pi 4 pi epsilon 0, the normal SI factor. This vector has coordinate 0 0 x y z, and this is 0 0 d, so this is the distance, and this is k q prime. Since the conducting plate extends is of infinite extent on xy direction, the potential will be symmetric about x and y, so it is useful to replace this by a single variable. This is kq rho square plus z minus d square to the power half. where we introduced rho square is equal to x square plus y square. This is the potential at any point P with z greater than 0. If we want to find out the potential on the conducting plate, so what we have, if we apply this condition, that is if we put z is equal to 0, the potential will be 0. So on the plate, so we have this one kq rho square plus d square to the power half plus kq prime rho square plus d prime square to the power half is equal to 0. This relation is valid for all values of rho. We assume that the point of observation lies very close to the very close to the origin. So rho, or if we consider the point D is not far away, then we can approximate it. This approximately gives you kq by rho 1 plus 1 minus d square by 2 rho square plus higher order term plus kq prime by rho 1 minus d prime square by 2 rho square plus higher order term is equal to 0, with the assumption that rho is greater than d and d prime. So we have expanded this in binomial theorem in powers of d square by rho square, and so this result will be valid for every value of rho. So the coefficient of 1 by rho gives you kq plus kq prime is equal to 0. That immediately leads to q prime is equal to minus q. And the coefficient 1 by rho cube gives you kq by kq d square plus kq prime d prime square is equal to 0. K can be cancelled and q is equal to q prime. So we have d prime square is equal to d square, which leads to d prime is equal to plus minus d. Now we have already taken d to be negative, that is the point lies on the negative z axis. If we further take d to be positive, then the image charge will be on the z is equal to plus half, which is in contrary to the method of images. So the acceptable solution is d prime is equal to plus d. So the problem, the two main problem was to find out the magnitude of charge q prime. It is the magnitude of the charge q prime, and secondly is the location of the image charge. It is the location of the image charge. So the problem is solved. We have obtained the magnitude and position of the image charge. Now the problem boils down to finding out the potential at this point due to the combination of charge q at A and q minus q at B. So the general potential is, now with this knowledge of Q and Q prime, we come to calculation of potential at R. It is KQ by AP plus KQ prime by BP with Q prime is equal to minus Q and D prime is equal to plus D. If we write it in Cartesian form, then it becomes the denominator is rho square plus Z minus D whole square to the power half KQ minus rho square plus Z plus D whole square to the power half and KQ. Here we have used D prime is equal to minus D. So this condition is applied here, and this is, so the sign is minus. This is the potential, and this potential satisfies all the condition imposed. It is 0 at D, Z is equal to 0. It goes to 0 asymptotically, because as you go far away the denominator goes to 0, so and the charges being finite, so the every condition is satisfied. If you differentiate it twice, you will find that it is 0 at every point except at this point where there is the charge. Now I come to the calculation of electric field. Electric field will have components x, y and z components. The x component of electric field is del phi del x. This is, we get by differentiating this, and the result is rho square Z minus D square to the power 3 by 2. This is x square plus y square, then half is adjusted, so twice KQ x, and for this is twice KQX rho square plus Z plus D square to the power 3 by 2. Similarly, the y component of the field can be found out, and the interesting thing is to find out the Z component of the electric field. The Z component of the electric field is, which is sorry, this 2 factor will not be there, 2 will be adjusted with this like this. This is the Z component of the electric field. If we want to find out the surface density of induced charge, surface density of induced charge on Z is equal to 0 plane. So this is given by, since if we consider a point at a distance rho away from the origin on the plate, it will have same value on every point on the plate, but irrespective of the angle. So S in general, S would be a function of rho and phi, which now reduces to function of rho only. Because if we consider a point rho at a distance rho away in here and rho away there, they are the same because of the symmetry of the problem about the z axis. and this is epsilon 0 Ez at z is equal to 0. This is the field. So if we apply z is equal to 0, okay, if we put z is equal to 0, these two terms there is a sign problem, that is z is equal to 0. If we put z is equal to 0, fine. Z is equal to 0. I have made some mistake somewhere. This is minus, and if we differentiate it with respect to z, something missing. Let me. Okay, at z is equal to 0, this is the numerator is minus kqd, and this is also minus kqd. So this is minus twice kqd divided by rho square 3/2. We can write it. Remember that k is equal to 1 upon 4 pi epsilon 0. So we can write it as minus q upon 2 pi d by rho square plus d square to the power 3/2. What is the total induced charge? Total induced charge or within a circle of radius rho in z is equal to 0 plane. So that means we are considering a circle of radius rho in xy plane. This is rho, and how much is the charge? So this can be obtained, that is q induced on rho. This is obtained by integrating thus with in this plane. So this is rho integrated over rho d rho d phi. The phi integration, since it is not independent on phi, the phi integration will give you simply 2 pi. So the quantity is q upon 2 pi times 2 pi. This is from phi integration and this phi is not, so let me write it theta, the angle. So this is the theta, and our remaining part is dqd, this d, and the remaining part is rho d rho by rho square d square to the power 3/2. We are considering a sphere of radius, a circle of radius rho. So this is the result. The result is minus qd, and if we substitute rho square by d square is equal to u, the result will be one by d minus 1 by d square plus rho square square root. This is equal to minus q 1 minus d d square plus rho square is square root. This part is less than 1 because this is 1 minus some positive quantity. This is less than 1. So the induced charge on this surface of the within this circle is less than the inducing charge. But total charge induced, Q induced with rho tends to infinity goes to minus Q is equal to Q prime. So the total charge induced on this plate is equal to the inducing charge. The one thing left is what is the force acts between this charge Q and the plate. So for the method of images is concerned, we can replace this grounded conducting plate by the charge Q prime and located at B. So it is the force between Q and Q prime, Q located at A and Q prime located at B. The force, so far force is concerned on the conductor will be pulled towards the inducing charge. That is all about the method of images where in connection with a system comprising of a point charge in front of a grounded conducting plate. Few related problems may be of interest. Firstly, we consider a dipole placed in front of a grounded conducting plate. To simplify description, we consider a two-dimensional picture. This is a grounded conducting plate, which is the Z is equal to 0 plane. We have a dipole whose moment is in this direction, so it comprises of two charges minus Q and plus Q. The center of the dipole is assumed to lie on the Z-axis. This is the Z-axis, this is the origin. So it is the charge A and the charge minus Q of the dipole, inducing dipole, is located at A and plus Q is at B. So the inducing dipole dipole moment P is equal to Q times AB. We write it Q times vector L. The image of this will be formed at A prime and the charge will be plus Q at A prime, and the image of this will be minus Q and will be formed at B prime. Again we will have a dipole, and this is the moment of inducing dipole. Now the moment of induced dipole in this case the dipole moment is from B prime A prime vector. If we resolve this dipole moment into two components, one is parallel to the plane, another one is the perpendicular to the plane, and similarly we can resolve this into one and these two components. You know that these two components are the same and the tangential component are the opposite, so a induced dipole will be formed. What will be the energy of the system? This can be considered to be the energy of mutual potential energy of two dipoles, one of moment this, another moment is this, and this would be their separation. This is the dipole in front of a conducting plate. Another interesting result is that we have two conducting planes. One is this plane, another one is this plane. These two both are the conducting plates, and we have a charge at this point. If we consider to be the x-axis and this is to be the y-axis, the point Q, charge Q is placed at AB. So this much is A, that much is B. Firstly, the image of this point A as from this point is at B, and it is minus Q located at B, and the coordinate of B will be minus AB. This image minus Q is in front of this, so it will produce an image over here, image charge of magnitude Q, and is located at C, and its coordinate will be minus A minus B. And finally, this charge is on the back of this plane and also of this plane, so it will not going to produce any more image. This point will produce an image charge minus Q located at D, where the coordinate of D will be A minus B. So if we want to consider any point in here, it will be a combination of the potential produced by all these four charges. That's all with image charge in connection with the grounded conducting plate. In the next session, we shall apply this method to a point charge in front of a grounded conducting sphere.